Assalamualaikum and hi everyone. Chapter 7 Chemical Bonding 7.2 Molecular Shape. At the end of this video, you should be able to explain valence shell electron pair repulsion theory or VSEPR theory. Draw the basic molecular shapes. There are 5 basic molecular shapes. The first one is linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And the last one, you should be able to predict and explain the shapes of molecule and bond angle in given species. Previously, we already learned on how to draw Lewis structure. Based on the Lewis structure, you can count the number of electron pairs surrounding the central atom. With the assumptions of electron lone pairs and bonding pairs in the valence shell repel one another. This will give the position of all atoms, therefore it will give you the idea on the molecular geometry of the compounds. This is called as valence shell electron pair repulsion theory. Molecular shape. Molecular shape is a three-dimensional arrangement of atoms in a molecule. It will affect the physical and chemical properties. The molecular shape is predicted by using valence shell electron pair repulsion theory or VSEPR theory. Valence shell electron pair repulsion theory states that the electron pairs in the valence shell of the central atom repel one another and arrange themselves as far as possible. Repel is when the electron pairs around the central atom is pushing one another so that they can arrange themselves as far apart as possible. There are 3 rules in valence shell electron pair repulsion theory. The first one is valence electron pairs surrounding a central atom repel one another. Thus, the bonding pair and the lone pair of electrons arranged themselves to be as far apart as possible. The second rule is the order of repulsion strength of lone pairs and bond pairs of electron is as follows. Lone pair and lone pair repels the greatest. Therefore, the bond angles between the bonding pairs are the smallest, followed by lone pair and bonding pair repulsion. As you can see in the molecule here, the bond angle increase slightly because there are only one lone pair here. And the last one is bonding pair and bonding pair repulsion. In these molecules, there are no lone pair. Therefore, this is the maximum bond angles between the bonding pairs. The last rule is a double and triple bond at the central atom is counted as one single bond to decide the molecular geometry. There are 2 categories of molecules. The first one is central atom without lone pair, and the second one is central atom with one or more lone pairs. As you can see here, the first category, the central atom has no lone pair at all. Therefore, all of these molecules will have a basic molecular shape. While the second category, there are one or more lone pair at the central atom. Therefore, it will not have a basic molecular shape. In this video, we are going to discuss about the first category of molecules with no lone pair at the central atom. Here is the 5 basic molecular geometry. The first class is AB2 with 2 bonding pairs at the central atom with no lone pair at all. Therefore, the electron pair will arrange themselves in a linear fashion. Therefore, the molecular geometry for this class is as linear as well. The second class is AB3 with 3 bonding pairs at the central atom with no lone pairs. Therefore, the electron pairs will arrange themselves in a trigonal planar arrangement. Therefore, the molecule will adapt a molecular geometry of trigonal planar. The third class is AB4 with 4 bonding pairs at the central atom with no lone pair. So the electron pairs will arrange themselves in a tetrahedral fashion, and therefore the molecular geometry of this kind of molecules is tetrahedral. The fourth class is AB5 with 5 bonding pairs at the central atoms with no lone pairs. Therefore, the electron pairs will arrange themselves in a trigonal bipyramidal arrangement. Therefore, the molecule will have a trigonal bipyramidal shape. And the last one is AB6 with 6 bonding pairs of electron at the central atom with no lone pair at all. So the electron pairs will arrange themselves in an octahedral arrangement. Therefore, the molecule will have a molecular geometry of octahedral. Remember that A represents the central atom while B represents terminal atom or bonding pairs. Let's have a look at each of these basic molecular geometry. AB2 with 2 bonding pairs and 0 lone pair at the central atom. As you can see here, the arrangement of electron pairs is linear. Therefore, the molecular geometry of this class is linear with a 180-degree bond angle. One of the example is beryllium chloride. As we can see here, there are no lone pair at the central atom, but we have 2 bonding pairs here. Therefore, the bonding pairs arrange themselves to be a linear molecular geometry with a 180-degree bond angle. AB3, 3 bonding pairs with no lone pair at the central atom. Therefore, the 3 bonding pairs will arrange themselves around the central atom in a trigonal planar fashion. The molecular geometry is trigonal planar with 120-degree bond angle. One of the example is boron trifluoride. As we can see here, there are no lone pair at the central atom, but we have 3 bonding pairs at the central atom with a 120-degree bond angle. Remember that planar means when you put the molecule on a flat surface, it will not stick out of the plane. AB4 with 4 bonding pairs and no lone pair at the central atom. The 4 bonding pairs will arrange themselves around the central atom in a tetrahedral fashion. Therefore, the molecular geometry for this class is tetrahedral with 109.5 degree bond angle. One of the example is CH4. As we can see here, there are no lone pair at the central atom, but we have 4 bonding pairs at the central atom. Therefore, CH4 will have a molecular geometry of tetrahedral with 109.5 bond angle. You can imagine tetrahedral similar to the tripod with a camera holder on top of it. Let's proceed to the next class of the basic molecular geometry, which is AB5 with 5 bonding pairs at the central atom and no lone pair at all. So the 5 bonding pairs will arrange themselves in a trigonal bipyramidal arrangement around the central atom. Therefore, the molecular geometry of this class is trigonal bipyramidal. Be reminded that there are 2 bond angles in trigonal bipyramidal. If I decide to color this atom with green and this one also with a green color, therefore you can see that the bond angle between the green atom and the yellow atom is 90 degree, while the bond angle between the yellow and yellow atom is 120 degree. You can imagine the trigonal bipyramidal molecular geometry as a fan with 3 blades suspended on the ceiling, and you put another string below that central part of your fan. Last but not least, AB6 class with 6 bonding pairs and no lone pair at the central atom. Therefore, the 6 bonding pairs will arrange themselves around the central atom in an octahedral arrangement. Therefore, the molecular geometry adopted by this class is octahedral with a 90 degree bond angle. For example, SF6. As you can see, around the sulfur atom, there are no lone pair, but we have 6 bonding pairs of electron Therefore, SF6 will adopt an octahedral molecular geometry with 90-degree bond angle. You can imagine octahedral molecular geometry as a 4-blade ceiling fan suspended to the ceiling with one string attached below the central part of your fan. Now you know there are 5 basic molecular geometry and how to predict the molecular geometry of a molecule. There are 3 steps of it. The first one is to draw the correct Lewis structure for the molecule, followed by counting the number of lone pairs on the central atom and the number of atoms bonded to the central atom. Number of atoms bonded to the central atom is also known as bonding pairs. And the last step is to use VSEPR theory to predict the geometry of the molecule based on the 5 basic classes of molecular geometry just now. VSEPR theory can also be used to determine the geometry of molecule with a double bond or a triple bond. A double bond and a triple bond has the same effect on the bond angles as does a single bond. Therefore, a double bond or a triple bond is counted as one bonding pair when predicting the shape of a molecule or an ion. In example, for carbon dioxide, this is the Lewis structure for carbon dioxide. As you can see here, carbon as the central atom has 2 double bond. Therefore, we can count each double bond as one bonding pair in order to predict the shape of this molecule. Therefore, carbon dioxide will adopt the AB2 class with 2 bonding pairs and no lone pair at the central atom. The arrangement of the electron pairs will be linear, therefore the molecular geometry of carbon dioxide is linear with a 180-degree bond angle. Before we proceed to the exercises, let's read our quote of the day. The strongest man in the world is he stands most alone. Henrik Ibsen. Before we end the video, let's try some exercises. Use the VSEPR theory to predict the geometry of the following molecules and ions. The first one is AlCl4-. You may pause the video and try it yourself before checking the answer. So here is the answer for AlCl4 minus. Let's try the next question, BH3. You may pause the video and try it yourself. So here is the answer for BH3. Now let's predict the geometry for NO2+. You may pause the video first and try it yourself. Here is the answer for the molecular geometry of NO2+. Now let's predict the molecular geometry for POCl3. You can pause the video and try it yourself. Here is the answer for the molecular geometry of POCl3. Let's predict the molecular geometry for XEF6 2+. You may pause the video and try it yourself. And here is the molecular geometry for XTF6 2+. Now let's try the final question, which is PCl5. You may pause the video and try it yourself. And here's the answer for PCl5. I hope you enjoyed the video. Thank you.